Hello, my name is Lucian Popa and I'm a research scientist at IBM Almaden. In our next segment, we will talk about the new challenges that are prevalent in data integration today, including the unstructured and large-scale nature of the data, along with the fact that we need an entity-centric understanding of the data. Let's start with an outline for the rest of this presentation. We'll first discuss and show through examples the new types of data that need to be accessed and integrated. This data lives mostly outside the enterprise, often in the public domain. It is unstructured, sometimes semi-structured, large-scale, and wildly heterogeneous. This heterogeneity can manifest either through differences in the structure or format of the data, or more challenging, through the differences in how the data is named or referred to. This is semantic heterogeneity. Even though the data is messy and wild, it is still potentially of very high value with the appropriate level of integration. So there is a stringent need today for tools or systems to build domain-specific entity-centric views on top of the raw data or documents, where entities can include, for example, companies, people, products, and various other types. However, there are challenges that one faces when attempting to build such entity-centric views. One such challenge that we'll focus here is the usability aspect. How do we make it easier? In particular, we will outline the need for higher-level abstractions and languages, which must be integrated with learning algorithms that help the various types of users. We will then survey some of the recent research on declarative languages for entity linking and integration. In particular, we'll discuss some recent theoretical foundations for entity linking, along with a practical language developed at IBM Research and used in various applications and customer scenarios. We will also look at some other interesting and related research directions. So let's start with the new types of data. We'll start with an example scenario published in a 2011 paper by Burdick et al., where the goal is to build entities from publicly available data. This data consists of many millions of documents that are required to be filed by publicly traded companies with two major US regulatory agencies, SEC and FDIC. The documents, which are mostly in text and HTML, sometimes in XML, are created by the individual companies and contain various types of disclosures regarding their financial performance, quarterly or yearly, their governance, including executives and directors, relationships with other companies, and more. For example, for a company like Citigroup, there are many thousands of documents, each focused on some particular aspects for some particular period of time, quarter or year. Instead of a document-centric view of the data, what we really want is an analytics flow that constructs entities and relationships, where one sees company entities and people working for these companies, along with the events that include like mergers and acquisitions or job changes, as well as relationships such as lender-borrower type of relationships. To build such entities and relationships, we first need to apply an information extraction component to derive various relevant facts, which are small structured records, from the unstructured documents. This is then followed by a complex entity resolution and integration phase where all these relevant facts and records that were extracted are then linked across the documents and then integrated to form unified entities and relationships. As an example, we show here a portion of the Citigroup entity, which is aggregated from the many source documents where Citigroup is mentioned. In this view, one can see and browse the important attributes of Citigroup as well as the relationships with other companies, such as subsidiaries, banking subsidiaries, competitors, co-lenders, and so on. And this is just one type of application. There are many other examples that appear in various domains. Continuing with our financial example, we can go now down one level of detail to illustrate the entity resolution challenge. If we want to put together a person entity, such as James Dimon, the CEO of JP Morgan Chase, we need to be able to understand and link all the mentions of James Dimon in the various documents. A key question in this context is, Do these mentions from the various parts of the text across the various documents refer to the same person? And this is challenging because there is variability in the person's name, there is a lack of a key identifier, and also the supporting attributes vary depending on the context. For example, sometimes James Diamond appears with his full title and affiliation, while some other times he's only mentioned informally as Mr. Diamond, and other identifying information has to be inferred from the context. Furthermore, people change jobs over time, and identifying them correctly over a longer span of time is challenging. In the end, all the relevant facts for an entity will need to be linked correctly and then integrated into one object. Stepping now one level up, and assuming that we have built the high-value entity-centric views from the raw data, we can now enable other types of analysis that exploit the rich entities and relationships in order to derive further insights. The same 2011 paper showed how one can perform systemic analysis at the level of the entire global financial system by constructing a network that connects all the major financial institutions that file with the SEC. The network is constructed based on the co-lending relationship, which measures the connection between two financial institutions via the number of commercial loans where the two appear together as co-lenders. By using standard centrality score computation, we can then assign scores to every member in this network, and this score will give an indication of how important or risky a particular member is for the global financial system. In this analysis for the year 2005, and also for subsequent years, the most central institutions were JP Morgan Chase, Bank of America, and Citigroup. While this is not that surprising, what is really interesting is that this global analysis is entirely driven by explicit linkages extracted from public data. Other types of relationships beyond co-lending can also be used to offer other types of insights, which can be important for financial analysts and regulators. Now that we motivated the needs to understand and analyze such public unstructured data, let's take a look at the main types of operations that are needed to build entity-centric views. First, we have information extraction, which is a prerequisite in many of these integration scenarios, and this involves extraction of the relevant concept mentions for persons, locations, job changes, and so on, from unstructured documents. We then have entity resolution, or ER, which amounts to matching or linking of the same real-world entities in one or more datasets. There are various flavors of matching of entities, depending, for example, on whether the data is semi-structured or structured. Here we show an example of matching social media data, which is often sparse and heterogeneous, with enterprise data, which is typically very regular and of higher quality. Entity fusion is another core operation which involves attribute-level normalization and fusion of multiple, possibly conflicting attribute values in order to construct a single entity, such as a person, out of the many records that were linked by the previous ER phase. Data transformation is also a related operation which can apply either before entity resolution as a pre-processing step or as part of entity fusion, where we need to transform the linked records into a target entity object. Data transformation is often covered by ETL, extract, transform, load type of systems. Finally, we have relationship identification, a more general form of entity linking, whose goal is to connect entities that are not necessarily the same, but are related by some type of relationship. For example, a bank can be connected by its parent to its parent holding company, or a person can be linked to its employer. So, what are the key challenges that are involved in developing such entity-centric operations or algorithms? Here we must also keep in mind that one usually needs a complex flow of such operations in order to construct a rich set of entities and relationships from the raw data. Historically, the main challenge has always been how do we make the development easier and more accessible to more types of users and not just experts. This challenge is now more stringent given the difficulty and the prevalence of the new data, but also given that most approaches require combinations of technologies and systems which are complex. So we have traditional ETL-like systems and database technologies, SQL for relational data, and XQuery or XSLT for nested XML data. And this can cover some aspects of data transformation. We then have dedicated, often black box engines for linking entities. Furthermore, we are seeing increased use of scripting languages, such as Pig Latin, Scala, Python, to take advantage of data parallel systems, such as Hadoop and Spark, for scalability reasons. But there are drawbacks. Data parallel programming and maintenance requires some serious expertise and also time. The combination of multiple systems makes it hard to reason. The integration logic is often lost among the physical operations and multiple systems. The development is not focused on the higher level entities, but rather on the nitty-gritty operations that manipulate the data while also worrying about performance and scale. So we need better abstractions and tools. One way towards better abstraction is to use declarative approaches. So let's take a look specifically at entity resolution and its need for declarative foundations. ER is actually a long-standing research problem. It started with a classical paper by Feligi and Santer in 1969. But over the years, much work has been devoted to the physical algorithms for matching and string similarity of the various types of attributes of entities, for blocking or partitioning of the sets of records into smaller groups in order to improve scalability, as well as for clustering of the similar entities. There are many surveys that describe this type of work. However, there is less work on the logical and declarative foundations for ER. In contrast, there are other related sub-areas that have greatly benefited from declarative specifications. And a classical example here is the language of conjunctive queries, which has been heavily used as a core foundational component for database query processing and optimization. Other examples include the use of constraints for consistent query answering in the context of data cleaning, and also the use of constraints to declaratively specify schema mapping and data exchange. In all of these cases, the logical specification expresses upfront the intended results, or the what, while the implementation, the how, is cleanly separated from the specification. And this in general gives the ability to reason about the system at the logical level, and also allows to have multiple implementations, which in turn leads to the ability to optimize across such implementations. So the question here is, can we come up with a declarative framework for ER systems with similar benefits? We now discuss some recent approaches that have started to focus on specification. This can be put under three categories. First, we have high-level languages, typically based on rules, which provide operational guidelines for how to match or fuse entities. A good example is Dedupalog, which uses datalog-like syntax to express combinations of hard and soft constraints, together with heuristics to minimize the number of violations of the soft constraints. In Dedupalog, the user must be aware of how the system interprets these rules or applies the heuristics. So this approach is not entirely declarative, although it is a step towards ease of use. We then have probabilistic approaches. A very general example here is the one based on Markov logic networks, or MLNs. In this approach, we write first-order logic rules, which, like in the previous approach, also provide a guideline for the computation of entities, but to be interpreted probabilistically. MLN-based approaches often require complex inference that is computationally expensive. Also, it is not always easy to explain the answers to a user. So a third type of approach, which can be seen as purely declarative, logic-based, uses link to source constraints to specify the intended properties of the links between entities. This gives rise to a formal and deterministic semantics based on certain links, which is a variation on the standard notion of certain answers. So let's take a look at an example of such declarative entity linking. Consider the scenario where we need to link subsidiary records in one database to their parent company records in a different database. More concretely, we need to link subsidiary IDs with company IDs. So first, we model the result of such entity linking as a binary link relation, which then needs to be populated with the correct links. For example, if we have these two source records for Citibank and Citigroup, we would like the link relation to contain a link between their IDs, given that Citibank is an actual subsidiary of Citigroup. We then use link to source constraints, which together with other types of constraints not shown here, implicitly define the link relation in terms of the sources. A link to source constraint gives a disjunctive enumeration of all the reasons for why a link can exist. In this example, whenever we have a link between a subsidiary and a company, it must be the case that one or more of these matching conditions must be satisfied. The matching condition can be as simple as checking the string similarity of names. For example, the fact we can check the Citibank is whether Citibank is similar to Citigroup, or can be more sophisticated and can involve existentially quantified conjunctions of predicates. In this example, the fact that there is an executive who works for Citigroup and whose title contains the string Citibank gives an additional reason for why we should link Citibank to Citigroup. Without going into further details here, this forms a logical specification that states the desired properties of the links, the what and not the how. So why is such framework useful? Well, essentially it allows one to reason at the specification level without worrying about the specific implementations or algorithms. For example, one can relate multiple entity linking specifications via static analysis of the constraints. In particular, we can also define notions of containment or equivalence of entity linking specifications. We can also analyze the expressive power of the entity linking frameworks under the various languages of constraints. And this is something that was pursued in depth in this recent paper by Burdick et al. In 2017. Somewhat surprisingly, probabilistic approaches can be captured by the declarative approach. And we have two such popular probabilistic approaches. First, the classical probabilistic matching by Felighi and Santer, which is now commonly used today in commercial products. And then we have linear MLNs, which are a particular form of MLNs that are useful for entity resolution. By exploiting such connection, we can actually transfer results and algorithms from one type of approach to another. For example, p-time algorithms, developed in the context of declarative entity linking, were shown to transfer to p-time results, which were not known before, for linear MLNs. More generally, this type of declarative entity linking framework can be seen as providing the rigorous foundations that are needed to build practical languages for data integration. So let's take a look now at one such practical language, and this is HIL, a high-level language for entity-centric operations that was developed in IBM Research over the course of several years. HIL is a fusion of multiple concepts from data integration research, which are then combined with programming language techniques. First, HIL includes concepts from the earlier Clio schema mapping work in the late 90s and early 2000s. It also builds on the formalism for data exchange, where one uses constraints to specify the relationship between a source and a target schema. Data exchange provides the foundations for declarative data transformation by telling us what it means to construct the best target instance based on a given source instance and a set of constraints. HIL also borrows concepts from the declarative entity linking that we just discussed. In particular, it uses the constraints-based specification for matching and linking of entities across datasets. Furthermore, HIL uses advanced programming language and compilation techniques It has a flexible type system which allows it to handle loosely structured and sparse data, and also deal with the fact that we can have data under many heterogeneous schemas. It also involves advanced compilation and optimization techniques to handle large-scale data. In particular, the same high-level entity-centric specification written in Hill can be compiled as efficient programs that run on Hadoop with MapReduce or on Spark. Hill is part of the IBM product called Big Match, and it has been used in many entity-centric applications. To give a brief example of Hill, consider a scenario of company matching across two regulatory agencies, SEC, which we have mentioned earlier, and FFIEC, which is another agency focused on regulating banks. Concretely, we must match bank entities from the FFIEC database to their counterparts from the SEC database. To express this in Hill, we use an entity linking statement, which has a SQL-like syntax, and consists of a union of rules to link the IDs of the records in the two datasets, followed by a cardinality constraint reflecting whether we want one-to-one, one-to-n, or n-to-n types of matches. Each rule combines various attribute-level matching functions, along with attribute normalization functions and possibly filtering predicates. In this example, Rule 1 is a statement to check that we have a match on company name, as well as a match on cities, modulo conversion to uppercase, and a match on the state province field. Note the use of a normalization function to standardize the state province values before we compare them for equality. Also note the use of a specialized domain-specific matching function for company names. This function understands the structure of the name attribute, including domain-specific suffixes and abbreviations, and is able to distinguish, for example, between a bank and its parent company. In general, for various entity types and attributes, there may be multiple such functions that are available for matching, ranging from simpler forms of equality and string similarity to more sophisticated functions that understand the semantics of the attributes. Coming up with the right combinations of such matching predicates is a challenge that also offers great opportunities for data-driven machine learning. In fact, there are two learning tasks here. We can learn the overall ER algorithm, that is the combinations of matching predicates to select in each rule, and we can also learn the attribute structure and variations, that is the logic behind company name match or the logic to normalize states or provinces. Also note that it is important that we learn using a target language such as Hill. Once learned or expressed in Hill, these entity-centric algorithms become reusable artifacts that can be ported, transferred, or customized across applications, datasets, or runtime platforms. Coming back to our key challenges, the previous learning observations lead naturally to a more ambitious goal, which is how do we scale this technology in general to a much larger class of users which are not programmers but rather subject matter experts. Under this setting, the system and the domain expert together co-learn the right algorithms. We must use data rather than code to interact with the expert, and we must also minimize the interactions while keeping it interesting. A natural methodology that fits with this view is active learning, which aims to identify the hard cases where the human input is required and from which the system can then learn. The main idea of active learning, which we illustrate now, is to extend a standard learning component with a feedback loop based on interaction with the human expert. The system starts by learning from an initial set of labeled data, which will then be extended through user interaction. We assume that the goal here is to learn entity resolution algorithms that match a dataset D1 with a dataset D2, and that the initial labeled data has been pre-populated to contain a few pairs of records labeled as match or no match. These examples are used to bootstrap the system, which will learn an initial ER algorithm A, expressed, for example, in the high-level language. The expert is now ready to give feedback on the learned algorithm A. But first, the active learning system must find interesting examples that capture how good or bad the currently learned algorithm is. Thus, in step 2, which is specific to active learning, The system issues multiple queries on the full datasets to find such examples. The intention is to find examples that identify potential problems with the learned algorithm so that it can be improved via the interaction with the expert. One applicable query strategy here is to retrieve potentially incorrect matches of A, as well as potentially correct matches that are missed by A. Once labeled by the user, these examples are added to the feedback loop and so that a better ER algorithm is learned in the next iteration. And this continues for several iterations until a good level of quality is achieved and there is not much more to be gained from the human expert. Some of the research challenges here include the ability to find a small set of good examples at scale, the design of the human-computer interaction, and ultimately the ability to achieve as good quality or better than the handwritten algorithms. Further details can be found in these two papers, but also in others. As we approach the end of this presentation, let us make some closing remarks and give some further pointers. A closely related area, which is quite important in practice, is that of data cleaning, also including inconsistent databases. We should point out that entity resolution or deduplication is an important form of data cleaning, with its own life as a standalone research topic. In terms of data cleaning, there is a lot more, and the interested readers can take a look at the various surveys. Coming back to entity resolution and associated data integration tasks, much work remains to be done with respect to learning of the various artifacts, whether they are rules, algorithms, or models. Some key points here that are worth reiterating are learning of reusable and readable artifacts is important. Having the human in the loop is important in order to take into account the domain knowledge of the expert. Also, data quality, explainability, and provenance are equally important. As a broader area, we have knowledge-based construction from unstructured data, which is a fertile ground that combines entity-centric algorithms with information extraction, as well as machine learning techniques, including deep learning, for link prediction or more general inference. We thank you all for your attention.